what I'm giving you here now is I want to go over the actual, what I feel are the 5, having done this for just a couple of years. I mean, it's not like I'm really experienced at this, but having done this for a couple of years and having looked up, I don't know, literally dozens upon dozens of free response questions on the internet, like you guys do too. I can tell you the 5 free response questions you're going to get, and I want to talk about them right now. There are 5 big concepts that will be covered in the free response. I'm not saying I know some of these will be covered. I'm saying every one of these. Something on thermodynamics, something, don't write any of this down. You're going to, like I said, you can watch this video. You don't really have to, your class has to watch this. But you'll have it there as a reference tonight, tomorrow, Sunday, to look at. Because I'm going to go over, just real quickly, this is like a crash course of what, you don't try writing this. Okay, crash course of each of these concepts that are going to show up on the free response. Guaranteed. Okay? Because how many free response are there? I told you. 7. So 4 of them are short free response, 3 of them are long. You are guaranteed to see these 5 concepts as part of those 7, pretty much. Okay? Now, of course, they're going to pop their heads up in the multiple choice as well. But let's try to concentrate on the big problems you're going to see. We'll start with thermodynamics. Okay? Do you remember Hess's law and the kind of questions you might get there? If it said, for example, I want you to make this equation from these 3 equations and tell me how much energy was released. Remember doing these? What would you have to do? Well, you'd have to reverse the guys that need to be reversed. CO2 is on the left. CO2 is here on the right. So what would I have to do with that guy? Flip them around and flip the charge, right? Sign, I should say. CH4, same thing. And so that's why it looks like this. Then you would cross out the guys who cross out, because they will. Like carbon will cross out, oxygen will cross out, and you'll end up with that thing. Sum them all up after changing their signs, and that's Hess's law. Don't forget, although these don't have a whole lot of them, if you need coefficients, you may have to multiply these numbers by something, correct? So say, for example, in this equation, let's go back and make it a little simpler. Say in this equation there were a 2 in front of that guy and a 3 in front of that guy. All right, there isn't, but if there were, I would have to then, for wherever I have him, I'd have to multiply that guy by 2, and I'll have to multiply the guy where I'm making CO2 by 3, as well as change the sign, okay? Remember that. That's Hess's law. That's one of the concepts you could see. You will see Hess's law somewhere on the test, but you could see on the free response. Other concepts from free response, from thermodynamics, I mean. Simple ones like this. Delta H, or actually now it's called, I would use Q equals MC delta T, right? Remember doing those? If you know the mass, you know the specific heat, you know the temperature change, and the temperature change to get the right sign is always TF minus TI, okay? If you get a negative sign here, is it endo or exothermic? Exo, okay, you should know that. I wouldn't worry too much about that. What I did is I just took the summaries of the review days from all the chapters, and I kind of just smashed them all up here yesterday over the course of a couple hours. So some of this stuff I'm going to kind of ignore. However, molar enthalpy information equation is another biggie, another concept you might see. So I ask you that right now, I know 90% of you probably are looking at that and saying, I have no idea what to do with that. What does it mean, write the molar enthalpy information equation? It means write this guy formed from his standard state elements. And you will know his standard state elements by either looking at Appendix K, where delta H is 0, or looking at the periodic table will tell you at least what state he's in. Carbon, for example, is yellow up there. He's a solid. You should know carbon's a solid. So I would have carbon, solid, and if you look in the back of the book, where he's 0 is graphite, plus, what's the standard state for hydrogen? It's a gas, but what would I write? H? H2, because he's diatomic and a gas, yields C2H4, right? Okay, and then I'd have to balance it. I'd need a 2 in front of there and a 2 in front of there, right? And that would give me, that is the molar enthalpy information equation. You look up at the back of the book, Appendix K, for us it was, they'll give you the numbers. And say you look up and the delta H of that guy is a positive 78. I'm just making up a number. Say it's a positive 78. What does that mean? The 78 is on this side, right? He basically absorbs 78 and he is endothermic, correct? What if you looked it up and it was a negative 100? It'd be plus 100 kilojoules of energy per mole, right? And he's on the right-hand side. And he will be exothermic, right? All of that stuff. Good. Now, on one other thing, for example, you can't balance molar enthalpy information equations by putting a 2 or a 3 in front of these. You're allowed to use, for example, let's take water. H2O, H2 plus O2 yields H2O would be a good example for water. You would normally balance that equation like this, wouldn't you? Right? But if you want a molar, if you want to know how much is produced per mole, 1 mole, you would have to do this. And by the way, get used to, although I have not stressed it all in Chem 1, but I've stressed it more this year, writing the actual symbols of the states down next to it. Okay? Get used to doing that. To balance this guy out, I would have to do this. See? Okay. Now let's go on. Next. Delta G problems. We all know this. Delta G equals delta H minus T delta S. All right, I already did one like that just a little while ago, just hinting about it when we were doing one of the multiple choice ones. So delta G equals delta H minus T delta S. If I have a negative delta H and a positive delta S, he is always spontaneous. If I have a positive delta H and a negative delta H, he is never spontaneous. You see, remember those? Because you know what favors spontaneity for entropy? More random, more craziness. You know what favors it for enthalpy? He wants to get down, to the lowest energy state. I drop this pen; it goes automatically to a lower state. What you have to worry about is when you have one or the other. If I have this guy saying one thing and that guy saying something else. Here, the enthalpy is saying, "I want you to be spontaneous." Here, I'm sorry. Yeah, he's saying, "I don't want you to be spontaneous." The bigger the T, the more effect he has. So at high temperatures, this guy's not going to be spontaneous. You see it? He's going to make this guy more important. So you'd be able to tell that. By the way, that's not what this question's asking. For this question, you just look up the values in the back of the book and solve it for delta H, delta S, and then plug them into the equation, which I hope you all can do that. Final temperature problems. If you mix two things together, remember those kind of problems? How many of those labs did we do, seriously, with the cups, right? At least 4, I think. We use cups, so. Now, in those kind of problems, you had to worry about MC delta T plus MC delta T equals 0. The sum of the two had to be equal to 0 because one of these guys is going to be negative. One of those guys is losing energy. It's got a delta H that is negative, that is exothermic. The other guy is going to be endothermic. He's going to be absorbing. He's going to be positive. Okay? His delta H will be endothermic because you added iron to water. If the iron was 87 degrees and water's at 20, you know you're going to get something in between those two. But you also should know something else, just a little common sense thing. Iron has a very low specific heat. Look at the specific heat of iron, 0.444 joules. What's the specific heat of water? 4.184 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. Remember that? All right, so you would expect that this temperature change is not going to be as great for water. It's hard to heat water up. It's hard to change its temperature. All right, it's going to be closer to, the iron's going to lose a lot more of his temperature. He's going to change a lot more than the water would. Bond energies. Very important to remember for bond energies, you don't just look up stuff in the back of the book. You got to keep in mind how many bonds. You got to draw them out sometimes. Like, for example, the CH4 bond. What do I have there? If I draw out CH4, it looks like this. So whatever the bond energy for C and H is, I times him by 4. But for chlorine, do I times it by 2? No. There's only one chlorine bond. Just one. So if I look him up, I've only got one bond. How about CH3Cl? H, H, H. I'd have 3 times whatever the value for the CH bond is, and then 1 times that value. All right? And by the way, these are the energies required to break the bonds. So when you're doing these guys, it's backwards. It's delta H of the reaction equals delta H of the reactants minus the delta H of the products. What are all the other ones when you're doing delta H and delta S? All the other ones are products minus reactants because it is the delta H of formation. This is the delta H for breaking the bond. Okay? All of this I'm going through much faster than you could possibly process, but if you were to look this up and look this over again, you would see. Now we're at kinetics. Do you remember how to do these kinetics problems? Okay? You watch this again. You stop this video when you're watching this tomorrow night or whatever, and you look up, okay, let me find some of those worksheets in my notes, and you see if you can go over some of the harder ones of these. Here, I'm giving you, there's like 3 ways I could ask these kinetics problems. Here, I give you the rate law expression. It's given to you. And I tell you the changes you're going to make. Well, first of all, the orders of the reactants are just the exponents. You should know that. It's a 1 for A, a 2 for C, and B's not there, so what is he? Okay? Like that. The overall order of the reaction would be 3, correct? Now, if I double A, triple B, and quadruple C, just look at it this way. I doubled A raised to the first power. I tripled B, but he's raised to the 0 power anyway, so who cares? And I quadrupled C raised to the 2nd power. 4 squared is not 8. What is 4 squared? 16 times 2 is 32. So that's how you do those. I don't have time to do a whole bunch of them, but that's how you do it. How about these guys down here? That's the other way I could do this. I just did one for you in the multiple choice of that previous test. Find 2 examples, 2 trials, where everybody's held constant but one guy. So here I have held constant, decreases by 1/2. What happens to that? Where does he decrease by? 9.6 to 2.4. What do you think? About 1/4, right? So if he's 1/2 to what power equals 1/4? Second. So this guy is going to be 2nd order. We know that. All right. Here I'm holding him constant. We have any place where it holds everybody else constant? Let's see. What other 2 can I take here? I know there's a place where I can do them. Anybody see it? 1 and 4. No, there's 2. Both guys are changing there. I know there's another one. Hold on. These are both held constant. 1 and 3. 1 and 3. All right, between 1 and 3. Here they're held constant. Here they're held constant. And here he's changing. Now he's going up by, it doesn't really matter because what happens to the rate? It doesn't change at all. So he goes up by like 1.5, but he doesn't change at all the rate, so he must be 0 order. So I now know he's 2nd order and he's 0 order. I can do the last one, and then I can tell the orders of all these guys. All right, so that's the second way I can ask these questions. More of those, kind of like that. If I were to graph, remember the graphs, you might want to look those over because we're going to talk a little bit more about graphs when we get to equilibrium. But why these graphs have the shape they have, look back over your notes on that stuff. All right, I wanted to get to the 3rd way. Remember, these kind of graphs you will see, you're guaranteed to see some kind of progressive reaction graph. What is that one, endo or exothermic? Exo, because it starts high, ends low, right? What's this value called right here? Activation energy, which we lower if we have a catalyst, right? That's what the catalyst does, lowers it. All those kind of questions. Look these over. You can pause it and look that stuff over. I don't have time to go over. That's pretty easy stuff. This is the other one I wanted to go over for the 3rd way I could ask mechanisms and rate law expressions. Here, I give you the rate law expression, and I ask you, is this consistent or not? Right? Is this guy consistent? I have a fast step where I use this guy once and this guy once, and I make this intermediate. And then I use the intermediate with this guy again. That's using him twice and him once. That's consistent. 2nd order, 1st order. Is this guy consistent? I'm using him twice and him once in the only step, which must be the slow step. Is that consistent? Yes. So yes, yes. Is this guy consistent? What's wrong with him? He only uses him once and him once, all right, in the slow step. Then the rest is fast, so that means he should have been only a 1 up there, but he's not. He's a 2. All right. So those are the other concepts here: collision theory, transition state theory. If they ask you to explain questions, and you want to do well on this test, when you get to this video and you pause it here, look up what is the collision theory, remember, and the transition state theory, and look that stuff up. Factors that affect the reaction rates, like powdering the reactants, increasing the temperature. What else? Concentration. All right, look up all those factors and catalysts. Remember this. This is, again, stupid that we have to memorize this crap, but basically we did do a lab where we graphed the stuff and we're able to tell which of these graphs tells the order. If you are able to do in one trial, you could actually tell. And you can. Zero order, first order, or second order depend on if I graph concentration versus time and I get a straight line. That means that there was no effect. Concentration had no effect. So there's a zero order. Here, the straight line will be the ln of concentration versus time, and here it is 1 over the concentration versus time. You have to look that back up if you want to see why. But a lot of times, it's just going to be a question of recognizing it. So you might want to just memorize those. I don't think I have them on your review sheet, but that's something you might want to look at again. All right, now we're at equilibrium. How much time we got? Okay, we got 15 minutes. Equilibrium. So we've done thermal, we've done kinetics. Very good chance you're going to see questions on, well, you're guaranteed to see questions on there, but also on the free response. Equilibrium. Is that an equilibrium problem? No, it's not. It went to complete. If it goes to completion, it's not an equilibrium problem. It does have the correct, because as the concentration decreases, the rate decreases. All right, but that's a reaction that's going to basically go to completion. Equilibrium will look something like that. You see the difference? Okay. What will happen is it'll never go to completion. It just kind of levels off. Now, at this point here, oops, it's at equilibrium. From there on, that's equilibrium. Okay? And you can determine, by the way, is this blue line, it can be a reactant or a product? It starts at 0. Is it a reactant or a product? The product. It's also written right here, too. And this guy starts at 1, right? So he's gonna, and he ends somewhere else. All right. Now, so if I were to ask you, what would the equation look like for this guy? Right here. H2 plus I2 yields. And by the way, do be careful. If they ask you to write something like this, make sure you put a double-headed arrow here because it's an equilibrium problem. Yields HI. And how many HIs? Yeah, I have a 2 there. So make sure you balance it. But here's another question. Would you predict that this reaction, as it's written, if I were to calculate the K for this, would this K be greater than, equal to, or less than 1? It went mostly to completion, right? It went close. So I would predict it's going to be greater than 1. It's a spontaneous reaction in the way it's written. Same exact reaction, graphed. What do you think this graph's going to look like? The exact same thing. Starts out with HI and ends up with H2 and I2. All right, and you can see by the fact that it didn't go very far, right? It didn't go very far. You would expect the K for this guy to be very small. K is going to be very small because what is K? K is merely KF over KR. It's the forward over the reverse rates. Okay? That's a ratio of that. All right? So you'll have other ones like that too. Now, what kind of equilibrium problems might you see? Let's take a look. I give you equilibrium is established in this guy. And by the way, one of the ones on your I saw people do wrong on the free response questions was for an acid. When we're talking about general equilibrium problems, you're right. Kc just equals the products over the reactants raised to their coefficients, right? So in this case, it would be K would equal NH3 squared over N2 times H2 cubed, right? But you remember, when we get to acids and bases, what do we leave out of the equation? It's usually like HCl plus water, right? Do we put water in there? Water's not there anymore. And when we get to KSP, we don't even have a denominator, do we? We only have the two products. So you're going to have to look that stuff over and remember. So that would be a real easy problem. You would just plug those numbers in, and don't forget, you got to you know, raise them to square them, do them right, the math-wise, but that's basically all you have to do for that guy. Here's another one. What kind of a problem is this? Take a look at this one. Remember, we did a lot of these back in the day. I'm told I have 2.4 moles of A and 2.4 moles of B in a 5-liter container. First thing to remember. What do you have to do with that 5-liter container? Divide by the size of the container. I don't know what that is. What's that going to be? Let's make up a number. 0.12. I don't know. I'm just making up a number. And 0.12. I'm just making this up. 0 and 0 I have initially. After equilibrium is established, this guy's going to decrease by some amount, that guy's going to decrease by some amount, that guy's going to increase by some amount 2x, and he's going to increase by some amount x. I have 0.3 moles of C. Right? Can I figure everything out without, a lot of you guys would try to start solving for x and doing the whole, you don't have to. You do not have to set up this whole problem. Because you know 2x equals 0.3, actually it equals 0.30 moles. What do you have to do with that again? Divide it by 5, right? Divide it by 5. And x would equal whatever it is. You plug him in for x and him in it for x. This is going to be 0.12 minus x, 0.12 minus x, right? And that is going to be your answer. Solve for k. Plugging all that stuff in with c squared d over ab. Again, doing all of chemistry in 30 minutes, 35 minutes. So you got it. That's, you know, you're going to have to look this over yourself and do some examples if you want to. Now here's one where you do have to solve for x, okay? Because you're told you have 0.2 moles of A and 0.1 moles of B are placed in, so that'd be 0.100 divided by 2 and 0.050 divided by 2 and 0. And then it says, it tells you what Kc is. And it's asking for the equilibrium concentrations. Minus x plus 2x. 0.100 minus x, 0.050 minus x, and 2x. So k is going to equal products c squared over a b. You must show that work. Show the formula. Don't just start throwing numbers around. They're going to want to see the formula. Plug it in. 2x squared, which, again, 2x quantity squared is 4x squared. And don't forget, at that point, you'd have to use the quadratic formula and all that stuff. Now, I don't think there's going to be a whole lot of that. That would have to be in what kind of a problem? Free response. You're not going to see that in a multiple choice. Okay. At equilibrium, this is more equilibriums, very much like that. Those are the main ones you want to look over some more of these, Kc and Kp. A lot of times, Kp is just not that, Kp is not that much different. Go back, look over a few of those, and also how they're related to delta G. Here is real good chance for multiple choice equilibrium problems. Okay, so watch these. What would happen if I increase the volume of this container? Okay, what would it favor? Would it favor the forward direction or the reverse direction or neither? Okay, well, they're all gases, and I pull back on my plunger. Okay, what am I going to do to the concentrations of everybody? Okay, here it is. They're all hanging out, and I pull back on the plunger. What happens to the concentrations of everybody? Same number of particles, bigger space, less, right? So it's going to favor the side with more molecules. It's going to favor that way. Which guy has more molecules here? That way. Who has more molecules there? They are not the same. Good, wrong answer, because he's a solid. It only applies to gases. So it'll be that way. Got it. Good. Make that mistake now, not tomorrow, not Monday. Decrease of pressure is the opposite of that. Well, actually, decrease of pressure is exactly the same thing. Decreasing the pressure is increase the volume. Exact same answers. Adding B to these guys. I add B to this guy. What happens? Goes forward. Favors the forward direction. And by the way, what's the name of this concept? French name? Yeah, Le Chatelier's principle. Good. All right. Good. It's going to go that way for that guy. Add B, it's going to go that way for that guy. How about increasing the temperature? Now, treat temperature just like one of the reactants or products. Here it's easy to see. Increasing the temperature is making this side too heavy, right? Going to go that way, correct? But it's not so easy to see here because I got to think. What does a positive delta H mean? Endo or exothermic? Endo. Endo means you've added it to this side energy. If I heat up that guy, if I increase the temperature of that guy, it's going to favor the forward to get rid of that extra energy. And finally, if this guy's an exothermic reaction, that means the energy is on this side. I heat him up, he's going to go that way. This explains some stuff like, from Chem 1, why sweating cools you off, why you get burned by steam. Okay, well, all those things about is partly Le Chatelier's principle. Okay, acid-base equilibrium. We're running out of time, so I could really shorten up the electrochem one. But acid-base equilibrium, you're going to have to be able to calculate for strong acids and bases. I can see there being multiple choice questions, not short answer questions, multiple choice, with easy ones like strong acids and strong bases. Strong acid and a strong base, very easy. If that's your concentration, what's your pH? 3. You see why it's 3? Because what does an acid do? A strong acid breaks up completely in solution. It reacts with water and forms hydronium ions and chloride ions. And if I put in 0.00100 moles of this, I get 0.00100 moles of that because 100% go that way. This is not an equilibrium problem. Okay? I can see that being, now, what if that were 0.00100 molar of NaOH? What would the pH be now? It's not that hard, people. It's not that hard. The concentration of the hydroxide would be 0.0. It's a strong base, right? That's the concentration of the hydroxide. So the pOH would be 3. What's the pH then? 14 minus 3, or 11. You see? And again, those are easy ones I should expect you could do. The harder ones get when you get. And by the way, what if I have AlOH3? What if it's a base like that? What do I have to do with the OH? And it's a strong base. Multiply that concentration by 3. See it? Okay. Calculating Kas or Kbs. All right. It's basically an equilibrium problem. The difference being when you write that equation for an HA plus water yields hydronium plus acetate ions, it is now an equilibrium problem. It's not going 100%. So if I'm given whatever I'm given here, I don't know, 0.01 molar of that, and I don't even care about water. He's not going to be in my equation. I have 0 and 0 of this, minus x, and plus x, and you solve it like a regular equilibrium problem. After that, the difference being Ka is going to equal hydronium times whatever the negative ion is over the HA, whatever he is, right? You do not include water in that. Got it? That's the one big difference. You might want to look over multiple ones of those if you can, where I can solve for pH, pOH, percent ionization, for all these kind of guys. All right, there are lots of examples of them. Acid strength, all I can tell you about that is memorize the ones that are on your sheet. But in addition to that, if you have binary acids, the further down you go, the weaker the bond, the better the acid. For ternary acids, it's the exact opposite. Okay. Also know how to name the acids. Definitely know how to name the acids. HBr. What's his name? Hydro. What's HCl? Everybody knows HCl, but you got to use your head. Common sense. I don't have to memorize everything. Every binary acid is named the same way. HCl, everybody knows HCl is what? Hydrochloric. So what's he? Hydrobromic. But if he's HBrO3, he's just bromic. BrO2, bromous. BrO, hypobromous. BrO4, one more, perbromic. Should know those. Okay? Should know those ions and those acids. All right. You should know these. You should absolutely know, especially in a multiple choice format, would be an easy question to have for a graph. Equivalence point is right here in the middle at 7. Looks like that. That's a strong acid, strong base titration. You should be able, you remember all the time. We spent like a week on these, and it feels like I didn't do them at all. You have to look these over. You got to look these over before you get there. All right? Because here the half the equivalence point, the pH equals to pKa. Why? Because the log of the salt over the acid, that's the Henderson-Hasselbalch equation, would be 1. Okay, so you wouldn't be adding anything to it. These are all the other possible shapes. Think about why they make sense. Look them over. Electrochem, we just went over. I'm not going to have to do all, but basically make sure you can do calculations like that, as well as, you know what I should do real quickly with you? We did that one just a few minutes ago. We did one like that anyway. Let's just real quickly, because we only have 4 minutes left anyway. What about these kind? Here, you would look up the guys who are, does it tell you more information on that one? Yeah, it tells you aluminum, silver, plate, blah, blah, blah. Diagram of cell. You would have to look up, and they would give you the standard electrode cell potentials. Okay, the potentials would tell you the guy who's more positive on that sheet is going to be the guy who stays at reduction. The other guy switches. All right, and if it's a battery like this is a voltaic cell, all right, you would diagram it. The guy keeping the guy who as more positive as the reduction, switching the other guy around as the oxidation. You're going to get, if it's a reaction that's spontaneous like this, you're going to get a positive voltage by just subtracting those two voltages. All right, and you should know how to diagram everything else about that. It doesn't change much. They're not going to ask you this year about whether the anode is positive or negative, but you should know which is which. Where there is reduction happening, if it's reduction over here, what is that? Wow, that's amazing. Reduction is the cathode, and that means he's adding electrons to the guy, right? Oxidation is the anode, and he is going to be giving off electrons, right? All right, so that's the other battery. That's the other cell we did not do. We did the other one just last period, and that pretty much takes us to the end. All right, I'm going to stop. I think that's the last thing I have. We did this also last period, right? Doing delta G equals NFE. Okay, well, I guess while I still have the camera rolling here, I'll just say one more time that I really think you need to look over these review packets. Okay, the stuff that I said to memorize on here, including most of these polyatomic ions, I realize I don't want you to spend, well, I'm going to spend all of Sunday just memorizing these polyatomic ions. That would be a complete waste of time. My guess is most of you know most of them anyway. You know, go over the most common ones. But the other stuff on here, you do need to commit to memory. And you've had these for weeks. Hopefully you have. And, of course, what should be helped by the fact that everything that's on here is stuff we covered already anyway. All right, that's basically it.